did PPP. He did also good calculation of second order perturbation, NP2. So a lot of small work he did, but eventually I think the Nobel Committee, if you ask me, Nobel Committee recognized him for Gaussian. Had he not met Gaussian, all these he would not have got Nobel Prize. That's my feeling. These are all highly difficult questions to answer, but people have told me that no, it is mainly for popularizing Gaussian. The way Gaussian has invaded. So, but water cone for different reasons, for DFT. And certainly, Popel did not work much on DFT, actually. Though Popel has used DFT in Gaussian package, but he himself did not develop. But Parr has developed, and Bob Parr always felt, I knew him very well, he's now very old, so he always felt very bad that he was missed out on the Nobel Prize. So Weitao Yang was actually Bob Parr's postdoc student or something like that, so he's now of course quite famous by himself. So yeah, Weitao Yang, the Li, Yang and Parr. Alright, so having done this, now I can, if I know some EXC, I can actually do a reasonable DFT, except this kinetic energy part, which is very important. As we discussed, kinetic energy is very important. Otherwise, everything else I can just do very simple. So here, for example, I will not write NDA anymore. This entire thing now can be replaced by VXC of rho. Whatever my EXC from there, I differentiate and get it. So VXC of rho, and that concept of exchange correlation potential actually came. But you remember from our discussion, it's a very complicated thing because it actually has a true two-particle density, an off-diagonal part for exchange, and a true two-particle part for correlation. So somehow these are basically parameterized to obtain such potential. But they have to have these features of what we discussed, Coulomb and Fermi hole, for parallel and anti-parallel spins. These features must be built in when I do the exchange correlation. Otherwise, the results will be significantly wrong. All right. As a final thing, I will now do Kohn-Sham DFT, just to give an outline of what this is done. Now, the reason initially many people were very unhappy because it actually made a departure from DFT. Because if you look at DFT, every term was a function of the density. What Kohn and Sham did was actually to bring back the orbital pictures. So that is why they call Kohn-Sham orbitals. And that was not the original idea of DFT. But obviously there was no other way to do kinetic energy. And the kinetic energy error was very large. So what Kohn and Sham introduced was basically, again, like a non-interacting. Now in this case, it is not homogeneous, but they're just non-interacting systems. So we know that for a non-interacting systems, you can always have a single determinant. That is known from the wave function. And from there, I can get density. So what Kohn and Sham assume that there is a model non-interacting system, and this is a very complicated thing which Mel Levy, in fact, you must know this person who did a lot of work in DFT, Mel Levy. Mel Levy said, and this is an interpretation, that for every interacting system, there exists a non-interacting system, model non-interacting system, whose wave function is different from the wave function here, but whose density is equal to this density. Now, this is a very complicated statement which many people have debated. Levy's constraint search theorem, these. So Levy said, although there is a non-interacting system from which I can get density, this density can mimic the interacting particle density, provided I find the right non-interacting system. And Kohn and Sham then said, here is the prescription of finding. So that is what they did. So how did they do? They said, I'm going to find orbitals which are really not non-interacting. They will be non-interacting only for kinetic energy. And then those orbitals will be found by a grand variation of the whole thing, which means those orbitals are including exchange, correlation, at least correlation in a proper manner, in some manner. So they are not really a non-interacting system. So this was a very radical idea of Kohn and Sham. So let me just write down. So essentially, Kohn-Sham says there are n orbitals. Or maybe I can say spin orbital, doesn't matter. chi. So there are n of them. They form so-called Kohn-Sham determinant, which has no meaning. The determinant is actually a fictitious determinant. But what is important is that if I have a single determinant wave function of n spin orbitals, then I know that my rho of r is nothing but sum over chi I star x, chi I x, integrate over d omega. So for example, if it is a closed shell system, so for closed shell system, I know that I have n by 2 spatial orbitals. Each of them doubly occupied, right? Each of them doubly occupied. Then my rho of r can be written as 2 times sum over I, phi I star r, phi I of r. The d omega just comes in as alpha and beta, so it just, the r is not integrated, that's the sum. So again, this is very easy to show. From integral psi star psi, we're integrating over all variables, only one of them will not be integrated, so that will remain, and this sum over I will actually make sure that this rho integrates to n. Okay, that also will make sure. For spatial orbitals, this summation will be over n by 2. For spin orbitals, it will be up to n. Spatial orbitals closed shell. So this is special model, but it depends. Whatever is the occupation, you can do that. So this can be easily generalized. The point is that the integral rho of r equal to n is automatically satisfied, assuming that all these orbitals are individually normalized. Phi star phi equal to 1. So automatically integral rho of r is equal to n. So Kohn and Sham said that if I assume this, then I can write the kinetic energy part of rho as a function of rho, not in terms of rho, but in terms of spin orbitals, which means I can write this just like I write in Hartree form, sum over I, chi I star x minus half Laplacian chi I of x dx. Remember our original theorem for the single determinant, that if I have Hamiltonian as sum of one particular operator, there is no doubt that kinetic energy is one particular operator. Then each first term would be written as sum of the orbital h orbital. So just sum of the orbital expectation values. So this is what is done. You just write the entire psi kinetic energy psi as sum of the orbital contributions from the half Laplacian operator. So this is a very important part. We said that if I write sum over h psi or psi h psi, remember my first term, it was h of ri, h chi I, h chi I, right? Plus half of antisymmetrized chi I, chi j. So remember, one of them was a Coulomb, one of them was exchange. I said that in the very first class. So this is what I'm doing. So I'm basically writing this for the kinetic energy only, not for the external potential. So that is something I know how to handle. So I'm writing it down in terms of the spin orbitals. Now the question is, you will again say that this is true if psi is single determinant. So this is where there's a lot of discussion. Mel-Levy said, for every interacting system, there exists a model non-interacting system whose wave functions are different, but whose densities are identical. So the assumption of the Kohn and Sham is that these orbitals have no meaning, but the density has a meaning. So how does the density become the exact density? Because if I know the function of exactly, I'm going to vary these phi i's with respect to, with not just Hartree-Fock energy, but the entire energy. Remember, in the Hartree-Fock, I also do the same thing, but there I write only Hartree-Fock function. What is Hartree-Fock function? H plus the Coulomb and the exchange here. This is Hartree-Fock. I am only varying with respect to this. So the idea of Kohn and Sham was that these orbitals, however, will be obtained by varying the entire functional. And if this is exact, then my density will be exact. The orbitals will have no meaning.
But so these orbitals idea are inspired by the Hartree-Fock orbitals?
Yes, the single determinant. The idea, so that's what I'm saying. This is basically a modern non-interacting system. So I have a non-interacting system inspired by the Hartree-Fock. Hartree-Fock is a non-interacting system. Okay, best non-interacting system. So it's a similar idea. That's the reason I can write the kinetic energy. But they are better than the Hartree-Fock orbitals, because in the case of Hartree-Fock, these orbitals are obtained by only varying this, which does not have a correlation. Here I am going to vary the entire thing, whatever I know.
But then, sir, there was, in Hartree-Fock theory, exchange was exact.
Yes.
But
Here exchange will be now LDA, whatever.
But there,
D3 leak.
but then we have taken an approximation for the exchange.
Everything is approximate. Yeah, of course. But the correlation is there now.
So correlation is contributing larger part than exchange?
Yes, many times. The exchange also is not that large. I mean, the Coulomb is much larger. Exchange is much smaller. They are very important, however. So the point that you are asking is a very important question. You are telling me that in the Hartree-Fock I at least do the exchange correctly.
Yes.
Here I don't do the exchange correctly, yet I take it bring in correlation. Now this is a point that I will right now not answer for the following reason. I have not told you how to get B3. So the fact that when they did the Becquet exchange, Becquet actually went much beyond LD, I told you, using grad rho, and they parameterized the correlation functional such that the whole thing is right. So it doesn't matter then what is exchange, what is correlation. So much of the exchange that you are talking has gone into the correlation. And that is the reason the original idea of writing EX plus EC is now gone. You just write EXC. Okay, so assume that that's a functional development. I will not go into it because that's a huge, it will require at least half a semester course if you want to really know how the functionals are developed. But assume that I know the functional. Then the idea is that I have an energy which is much beyond Hartree-Fock. This is the exact functional. So the orbitals that I would get would be different from Hartree-Fock orbitals. I'm not saying these orbitals are better or worse, but maybe his interpretation is that the density obtained from those orbitals is exact, not the orbitals. Yes?
So computationally we are back to the square one, right?
Yes.
Because
Yes.
there
Yes.
we had a advantage of getting density, now I have to get all the orbitals.
Oh, absolutely, absolutely. That is the price you paid. So that is the reason they say Kohn-Sham DFT is just like Hartree-Fock. Just change the potential. The Fock operator is different. And I'm going to write that down. Actually, very immediately. So yeah, if you have the Hartree-Fock program, you understand the DFT. Because the Fock operator is of course different now. Because you have the different exchange correlation. Correlation was missing, exchange has come. So that's all the difference. Rest everything is same actually. So I'm now going to write down first the energy. So I'm going to erase this part and going to write this as EXC of rho. And then I'm going to erase this part and I'm going to write this as sum over I chi I star minus half Laplacian chi I, which is over the spin orbital, but I can integrate the spin trivially if it is closed shell. So I can write this as 2 times sum of the spatial orbitals, just like you normally would do. But that's a very minor point. Right now I keep it in spin orbitals. So this becomes now my Kohn-Sham functional, Kohn-Sham theory. I will not say functional. The functionals, of course, is dependencies. So there is nothing called unique Kohn-Sham theory. Kohn-Sham is only for kinetic energy. Now within Kohn-Sham you can have B3 lead, you can have BP91, then PW91, all kinds of functionals, depending on how I do XC. So XC is something that I short everything that I don't know right now. In fact, you may also argue that this part is also not right because this is from a non-interacting system. So how can this be right? It cannot be exactly kinetic energy. Yes, that is why Thomas Fermi said, the Kohn-Sham said, there is a residue error of kinetic energy. That residue kinetic energy error is also shoved here. So when they actually model the XC, now I'm going to model XC by parameterizing anyway. So I don't care. My benchmark is exact numbers. So that means whatever error I have done, that is called Kohn-Sham errors. is also included here. So Ex is not just Ex plus Ec, but also the kinetic energy, some amount of kinetic energy is coming. Well, everything is not parameterized. So this is where DFT has a problem. Because you say, if you are parameterizing, then what are you doing? Yeah, that's a problem. But if you understand how they are parameterized, and this is a matter of detail, it's not so bad. There is a science to parameterize. Like using grad rho, using the correlation functional, using the idea of Coulomb hole. So the parameterization they have brought in science, so it is not just totally mindless. Okay, yet they have to do parameterization. So everything is shoved here. If that is so, then I can now write what is called the Kohn-Sham DFT equations, which of course have to have n orbitals. So that is what I will write, and probably I will end at that point. So now I have a chi-i's. The only thing I have to remember is that this rho of r is equal to sum over I chi-i square. This is something I have to remember. So I need to now, just like in Hartree-Fock, impose a normalization term for chi-i. Just like in Hartree-Fock. What is the normalization term? The chi-i chi-j equal to delta ij. So instead of density normalization, integral rho of r d cube of r equal to n, I am going to introduce chi-i chi-j equal to delta ij, because now this and this together is going to ensure that rho of r integrates to n, right? Because if those are integral chi-i star chi-1, then sum over n, it will essentially mean rho of r integrates to n. Right? So once again, I just want to write this up with an integral over d omega, to be more precise. The omega integration is already included in our rho of r definition. Okay. So this is something that I have to remember. So in my Lagrange multiplier with this will actually come. Just like in Hartree-Fock. This comes in Hartree-Fock also. So my Lagrange multiplier now becomes L of rho is E of Kohn-Sham rho minus sum over ij lambda ij chi-i chi-j minus delta. Please note that now there are n square constraints for each I, each j. So there are lambda ij metrics. Okay? So for each constraint there is one equation, one multiplier. So I am going to now vary this. So the variation is done not directly with respect to rho, but with respect to chi-i star. So I want to vary the Kohn-Sham orbitals. So how do I write this? Each time I will write this using the calculus of variable. I write this as del L del rho, wherever rho is directly there, into del rho del chi-i star. Assuming the chi's are 2 times phi star, I can write everything in terms of r. So this is not very difficult to do. You can see that del L del rho I can already write for these terms, and each term I have to multiply the chi. So this is very easy to do, because if I differentiate with respect to one chi-i star, one chi-i will remain. It's a delta ij, so it just remains, though integration, again the same idea, differentiation and integration, so only chi-i will remain, and I can write down the Kohn-Sham equation trivially. For the kinetic energy part, I am not going to use this. So for the kinetic energy, I have a direct expression of this. So I have no problem. And then I can write what is called the Kohn-Sham DFT.